Hello everyone, I'm Xuting. Today I'm presenting Rethinking Machine Learning Collective Communication as a Multi-Commodity Flow Problem. This is a joint work with Banas, Siva, Liangyu, Vincent, Miguel, Srikant, and Luke. Machine learning models now are getting larger and larger, so people now have to distribute model and data across multiple GPUs, and possibly in many nodes or servers. As models get larger and distributed, the amount of communication required between GPUs also increases. For example, one common scenario of such communication is in a data parallel training pipeline where GPUs want to sync greetings across the group. They would perform a collective communication primitive called allGather to collect greetings from each other. The collective communication process could be very costly. What's even worse, they do not use the network efficiently. As a result, data shows that GPUs can spend as much as 20% to 65% of time idle waiting on network communication. So, what is collective communication that causes this bottleneck? There are many collective communication primitives that are used during different stages of a machine learning pipeline. Each of the primitives specifies the data each node wants to share, which starts at its input buffer, and the data each node wants to receive, which would end up in its output buffer. Let's take allGather as an example. Each node starts with one chunk of data that this node wants to share with everyone else. And when the allGather primitive completes, each node now has a piece of data from every other node in the group. This can also be expressed in this demand matrix, where row 1 shows that node 1 wants a chunk from node 2, node 3, and node 4, and so on. A scheduler will do some offline planning to come up with a communication schedule, instructing each node what, where, and when to send. This determines link utilization, queuing, and ultimately how fast to complete a collective communication. For example, a simple ring schedule would instruct each node to send to its neighbor at every epoch. At epoch 1, node 1 would send this blue chunk to its neighbor at the top, and node 2 would send this yellow chunk to its neighbor to its right, and so on. After epoch 2, epoch 3, and at the end, we finish this allGather in 3 epochs, each taking us alpha time plus chunk size over bandwidth amount of time. This alpha is link latency, an important part in our modeling, especially when chunk size is small. This is a beautiful schedule, but we can notice that some links in the center are not used at all. And things like this get much more complicated when we get a larger and topology with heterogeneous links. In short, pure algorithm-based schedules often tries to map a fixed schema to our target topology, like a tree or a ring, as we just saw earlier. This causes underutilization of links and is inflexible when data size changes. To get better solution quality, which usually means using more links and better routing, researchers developed schedule synthesizers that precisely model the topology, input, and output. And the tailored fit schedule is indeed much more efficient than traditional ways. But because synthesis is NP hard, the time and resources required to synthesize a schedule increase exponentially. And MCQ, for example, cannot find a schedule for multi-node topologies. And this is in reaction to this important scalability concerns. A second class of approaches falls back on increasingly rough heuristics to find the solution more quickly. Unfortunately, these heuristics sacrifice considerable performance to simplify the problem. In this work, we argue that it is too early to give up on near optimal solutions for collective communication, and it is possible to achieve scalability without sacrificing quality. Our inspiration that gives us hope is the subfield of traffic engineering, an important subfield of network management. The problem of traffic engineering share a lot of similarities as collective communication. We both have a topology as our input, and we both have a demand matrix. And we are trying to solve a problem of resource allocation, where we allocate flows onto links to demands such that we do not exceed capacity anywhere, which means these two problems could share constraints in a mathematical formulation. Even if we drill down to the objective function, we can find they have similar objectives, like to maximize utilization, the amount of traffic served, or to minimize time. And there's tons of advantages of framing the problem in a traffic engineering way. First, traffic engineering has been studied for decades in networking, and there's years of research we can pull from. And we have deployed traffic engineering solutions in large production networks. And traffic engineering solutions can be scaled to more than 100 nodes topologies, which is the scale we need for today's machine learning networks. And we know how to solve traffic engineering problems optimally, which means we can possibly get better quality schedules by using traffic engineering. This leads us to TICO, Traffic Engineering-Based Collective Communication Library, which speeds up collective communication more than 2 times compared to previous state-of-the-art. TICO also offers better scalability compared to previous solver-based approaches. Let's dive into how TICO works. And it's important to note that I've discussed similarities, but in reality, there are critical differences that make a direct application of traffic engineering not possible with collective communication. In a classical routing problem in traffic engineering, we have nodes, edges, and demand matrix as our input. And our goal is to find the assignment of flows on the edges that maximize the objective while making sure that it's feasible. By feasible, we are enforcing 2 constraints. The first is capacity constraints, which means that we cannot exceed capacity of any link. And the second is a flow conservation constraints, which means we cannot create flows out of nowhere. In order to adapt traffic engineering to collective communication, there are 4 important changes to make. First is latency and queuing. Second is in-network copies. Third is deserialized sends. And the fourth is support for storage and caching. I will be focusing on the first 3 changes in this talk. So one important difference between traffic engineering and collective communication stems from the fact that in collective communication, we are sending chunks, which is a fixed amount of data, while in traffic engineering, we are dealing with a stream of traffic. Here we have an O2O collective communication demand matrix, where it is very similar to OGather, except for that now each node wants a distinct chunk from every other node, making them to have more data in their input buffer. We can immediately notice that this demand of O2O communication is very similar to this demand matrix of this multi-commodity flow problem. But it's important to notice that in traffic engineering, the demand matrix specifies the node wants a stream of traffic, D21 from node 2, and this Dij is in bits per second. While for collective communication, node 1 just wants chunk C21 from node 2, and this chunk is a fixed data rather than a stream of traffic. One important implication from this difference is that we need to add precise delay modeling to traffic engineering in order to support collective communication. Let's see how traffic engineering models delays. Traffic engineering just takes a maximum of delay between the source and destination, and we can simply add up the delay of alpha between source 1 and destination and compare that with source 2 and destination. So notice that we have set alpha 2 to 3 alpha 1 plus 2. And this simply leads us to the maximum to be 3 alpha 1 plus 4. This is simple because traffic engineering makes fluid flow approximation as demands are fixed and sustained. And traffic engineering just uses delay as the maximum end-to-end transfer time across all paths. However, this approximation is not accurate in collective communication. As we can see in this case, if this blue chunk and dark blue chunk arrive H3 at the same time, they have to queue and wait for one chunk to be sent to D first, and then another chunk can be sent. This adds to our latency. So our correct delay estimation is 3 alpha 1 plus 3 plus 2. This seemingly small differences can have rippling effect in our schedule. So we have to model everything as accurately as possible. In order to model delay in flow conservation constraints, for simplicity, we can just assume node 1 is not consuming chunks and has a large buffers. And the flows arriving at node 1 is carrying source S bits at epoch K. So we can have our constraints structured by the flow that comes in at time K plus what's in the buffer at time K, and that would equals to what's in the buffer at K plus 1 time, plus the flow that goes out at K plus 1 time. So this completes our flow conservation constraints with delayed modeled. Second, we need to model network copies, and this is an important property for all gather to have. For example, the source wants to send this blue chunk to 3 destinations. Without the ability to copy, the source needs to go to D1, D2, D3 separately. But our GPUs has the ability to copy and caching stuff. So it can complete this all gather schedule in the simple one step. And the difference with copy is we can complete the schedule in 2 seconds. Without copy, we have to spend 4 seconds. So traditional flow conservation constraints doesn't hold when we are making copies. So we have to model the flow conservation constraints. And we can model it in a way that to add what's in the buffer at time K plus the flow that comes in by time K, that will be greater than or equal to the maximum of the flow that goes out on each link in time K plus 1. And this is our new flow conservation constraints with ability to make copies at nodes. The third thing is that we now need to track each chunk in the network if we are allowing nodes to copy. So far, we have not tracked what part of the chunk we received, but in OGather, it is necessary. Consider this simple network with 4 nodes interconnected. Data is moving from node 1 to other nodes in the network, and it is possible that node 1 splits the chunk into 2 pieces. And now if we allow partial chunks and copy at the same time, we run into a situation where the optimization can send the same copy of part of chunk to 2 neighboring nodes as they also need the data, and they can forward it along to the next node. Since the formulation has no way of knowing these 2 halves are the same, node 4 now thinks it has received the full chunk. All our optimization constraints are satisfied, but node 4 has actually only received 2 same halves of the chunk twice, which doesn't complete the all-gather demand. The solution is that we need to incorporate integer variables into our modeling. This allows us to track each individual chunk through the network. We do not allow chunk to be split anywhere in the network. On each link, either the whole chunk is sent or it is not, which is done by setting the flow variable to either 1 or 0, but nothing in between. We can increase the number of chunks to decrease the size of each individual chunk and support smaller transmission blocks. But this introduces a trade-off between it increases the number of variables and slows down the optimization, and users can do this sitting in the problem setup stage. These 3 changes, along with the 4th one that is skipped but very simple, completes our all-gather flow conservation constraints, which states what's in the buffer of chunk C at time K plus the flow of chunk C that comes in by time K is greater than or equals greater than or equals to the maximum of the flow of chunk C that goes out on each link in time k+1. More details about our features and our formulations, including our objective function that includes an A-star algorithm that further increase our scalability, can be found in our paper. Moving on to our evaluations, we compare our performance against TACO and RECO. We compare solution quality and solver speed as well. We ran large-scale simulation and hardware experiments with all-gather, all-to-all, on public commodity topologies like NDV2, and our internal topologies that are up to 256 GPUs. When we compare solution quality with TACO, the y-axis is our improvement in algorithm bandwidth over TACO, and we can notice that TICO is best at larger scale when there are 4 chassis, and is better at all-to-all communication, probably because traffic engineering is more natural with all-to-all. With scalability, we compare our solver speed, and with 256 GPUs, TICO is able to generate an all-gather schedule in 2.8 hours, and this setting was not possible with TACO. For our hardware results, we are running on 2 chassis of AMD MI250 topologies on all-gather schedule. The left axis is algorithm bandwidth, which reflects the efficiency of our algorithm. We can notice a 3 times speed up over RECO when the buffer size is 1 megabytes, probably because this is a sweet spot where neither latency nor the bandwidth cost is overwhelmed by the other one. For our challenges and future directions, we are working on improving lower into the hardware, handling failures, and supporting for other collectives. This concludes my presentation on TICO, where TICO modifies the traditional traffic engineering to formulate the collective communication problem, and TICO achieves better scalability and solution quality. The code of TICO is available on GitHub.